Hello, this is Dr. Gardner. We're going to continue talking about atoms and ions and isotopes today. However, we're going to look a little further into atomic mass and relative atomic mass and how they differ, and then how we can connect the idea of isotopes and a mixture of isotopes to these two values. Then we're going to be looking at how we can predict the formula of ionic compounds based on looking on the charge of ions that we can predict by their locations on the periodic table. Now, the types of skills you'll need to understand this lecture were developed in our last several videos, including when we discussed how to classify elements on the periodic table and how to predict their charges from their groups or columns on the periodic table. Also, I'm assuming that you have also watched the video on how we can predict the subatomic particles in isotopes and ions. So with those in mind, if you've already watched those videos, then this is the video you want to watch next. What we're going to be looking at first is atomic mass and how that relates to relative atomic mass. So first of all, we've been writing mass numbers or atomic masses for isotopes for the last couple of lectures. And so with respect to writing those atomic masses, those are for just a single atom, right? And my mass number is going to be equal to my number of protons in the nucleus plus the number of neutrons in the nucleus. We don't worry about the number of electrons outside of the nucleus because they contribute very little mass in comparison to the neutrons and protons to that atom. But if I look at a mass number for a carbon-12 isotope and relate that to the mass number for a hydrogen-1 isotope, well, the carbon-12 isotope is 12 times the mass of a hydrogen-1 isotope. Okay, if I consider an oxygen-16 isotope, it happens to be 4 times the mass of a helium-4 isotope. Okay, so we can readily relate mass numbers to compare these ratios. So it took the mass of 12 hydrogen-1 isotope atoms to add up to the mass of 1 carbon-12 isotope. It would take 4 helium-4 isotopes to add up to the mass of an oxygen-16 isotope. So that works really well if we were dealing with pure samples that contained only one isotope. However, in nature, we actually have mixtures of isotopes that can occur in nature. And so when you look on the periodic table for the mass underneath the symbol of the element on your periodic table, you'll notice that you don't get nice whole numbers. That's because you often will have a mixture of several different isotopes. If I look at hydrogen, for example, we'll see that the mass shown underneath the element hydrogen on the periodic table is a little greater than 1. That is because we have a small contribution from hydrogen-2 isotopes and hydrogen-3 isotopes. We sometimes call the hydrogen-2 isotope deuterium. Sometimes the hydrogen-3 isotope is called tritium. But since we have very small quantities of those other isotopes in nature, what we see below the element symbol is actually a relative atomic mass, which is really the average mass weighted by percent of the mixture of isotopes we would find in nature on Earth. Okay, so that's why we're not getting whole numbers as we look at the periodic table. We're not just considering one single atom, which would be a specific isotope. We're considering a mixture of many atoms that you might be working with in the lab when you weigh out gram quantities. And so we have to consider that average, basically mass, as we have the percentages of all the isotopes that are occurring in my sample. So realize when we look at these mass numbers, they are related to a single atom, a single isotope, and so when we scale it up to larger quantities like gram quantities, we have to use that relative atomic mass on the periodic table. These mass numbers are also not equal to grams, but I'll show you how we can convert them to grams with a conversion factor here in a little bit. Now, how in the world do we find the mass, though, of a single atom, or a single ion, or a single molecule? Well, unfortunately, we can't just go to the lab and take a single atom or molecule or a single ion and weigh it on a scale. The problem with that is our scales in the laboratory are nowhere sensitive enough in order to weigh single molecules or atoms. We have to have larger quantities on the gram scale or milligram scale or at least microgram scale, depending on the specific scale I have, in order to take readings. Okay, so how do scientists, how do chemists study specific molecules or atoms to find what mass they have? Now, we'll determine their masses in atomic mass units. So one atomic mass unit would be the mass of a hydrogen-1 isotope. 12 atomic mass units would be the mass of a carbon-12 isotope. The atomic mass unit is actually defined as 1/12 the mass of a carbon-12 isotope. So I have to have some special instruments in order to determine masses of individual atoms or ions. One of these potential instruments we can use to find the masses of these very small particles, such as atoms and ions, would be a mass spectrometer. So if we use a mass spectrometer, we can actually find an individual mass of an isotope. Or if I have a mixture of isotopes I introduce into the mass spectrometer, we can find the ratio with respect to percentages of each of the isotopes in that mixture. So let's say we want to analyze a sample of neon. Okay, what I can do is place the neon sample into my mass spectrometer, and when in this case it's a gas, but if I have a sample that isn't a gas, oftentimes we'll have to introduce these samples with a nebulizer, and so that we get very small droplets, evaporate any solvent that might be present in the sample, and then have very small particle sizes of individual atoms or ions that have been separated in the nebulization process. But in this case, where we're already in the gas phase, we have a lot of space between the neon atoms. If we look on the periodic table, we can see neon doesn't have a nice whole number either, right? So we're looking at about 20.17 for the average atomic mass for neon. Let's see where that's coming from. If we introduce neon into the mass spectrometer, we basically have an electron beam that knocks electrons off of the atoms in the gas phase. This ionizes my neon atom. So even though it takes quite a bit of energy to knock electrons off of a noble gas because they're so inert, we can do so with sufficient energy. As we do so, we form neon cations, and then we basically have charged plates that we accelerate the charged particles from the entrance of the mass spectrometer. We accelerate them due to an applied voltage on these plates that accelerates the charged particles that are positively charged from loss of one electron. And then we go through a magnetic field. Now there's a variety of ways of producing the magnetic field, but once we produce that magnetic field, what happens is we have different curvature in that magnetic field of the particles that is related to their mass and their charge. So basically the mass and charge ratio allows me to separate out the different atoms or molecules that have formed cations into slightly different curvatures that will strike the detector at different angles. So we're able to scan with the detector and find the quantity of slightly different masses, even in the atomic mass unit scale, which I wouldn't be able to measure on the scale in the lab, but here I can measure it with the mass spectrometer. And we'd find with the neon sample that the majority of it is actually fairly light neon 20 isotopes compared to the neon 21 and the neon 22 isotopes. You notice the lower mass, lighter isotope has more curvature in the magnetic field with its smaller mass. They all have the same charge. They've all lost one electron to form a +1 cation. So the lighter particle curves more in the magnetic field, and there's less deflection in the magnetic field for the heavier particles as they pass through the magnetic field. So we were able to analyze with the mass spectrometer and find that 90.5% of neon is present as neon 20 isotopes in nature here on Earth. And so we can determine then why the mass for neon is fairly close to 20. However, we do have about 0.3% of neon 21 isotopes and about 9.2% of neon 22 isotopes. So that's why our mass, which is called our relative atomic mass, below the element symbol for neon on the periodic table is a little greater than 20 because of the components of other isotopes in a bulk sample. Okay. You can see that a little better here with respect to the 90.5% of neon 20, the 0.3% of neon 21, and the 9.2% of neon 22. Okay. Now, when I start talking about atomic mass units, sometimes especially in biology courses or in other fields, we might refer to these as Daltons. Okay. An atomic mass unit, though, is 1/12, as I mentioned before, the mass of a carbon-12 isotope. Now, an atomic mass unit, if I want to relate it to grams, is a very, very small quantity because we're talking about a single atomic mass unit. This would be like the mass of a hydrogen-1 isotope. Very small, or 1/12 the mass of a carbon-12 isotope atom. And so we would have a very small mass, as you would expect, of 1.6606 times 10 to the negative 24th grams. This is expressed in scientific notation, so realize that negative 24 means the number is very small. To convert it to a standard number, I would take this decimal point and move it to the left 24 times to generate the mass in grams. So it's a very tiny mass. So for convenience's sake, we often will refer to, when we're discussing a single particle that's small like an atom or an ion or a molecule, with atomic mass units, and we'll only convert it to grams if that's useful for us, but you might run into a problem like that on the homework, and this is the conversion factor you would use. One atomic mass unit is equal to 1.6606 times 10 to the negative 24th grams. We may have to do that in the course when we cover chapter 1 or chapter 4, so this is a useful conversion factor to remember. That's usually also in the back of most chemistry textbooks, with common conversion factors shown there as well. So since it's 1/12 the mass of a carbon-12 isotope, then carbon-12 isotopes have a mass that's exactly 12 atomic mass units. Okay? Now, in nature, though, we have samples that consist of many atoms, which can be a mixture of isotopes, since we have a bulk sample that's in gram scales. And so our relative atomic mass, as I mentioned, underneath an element symbol on the periodic table, is actually taking into account the relative amounts of every isotope in that mixture that's a bulk sample you might be weighing out. So if we look at a bulk sample of carbon, well, in nature, we end up with some higher mass isotopes in the mixture, and so the relative atomic mass you see on the periodic table below the symbol for carbon is a little greater than 12, even though the carbon-12 isotope is the most abundant isotope. The isotope we have the most of in a sample, there are some heavier isotopes present in much smaller percentages, and so when we look on the periodic table, we see 12.011 atomic mass units. That's just telling me that a bulk sample would have some of these other heavier masses of isotopes on Earth in the mixture, which would give us a relative atomic mass in the mixture on average of 12.011 atomic mass units. Now, this is a value I use when I have larger sample sizes. If I just as a single atom, well, I would use the isotope mass, of course, for that specific isotope, but usually in the lab you won't be weighing one atom at a time. You're not using a mass spectrometer in this course, but you definitely would have to relate to gram quantities. So I would use this mass off the periodic table to do some calculations, as we'll see later, relating that mass to gram quantities and what we call moles, that you will see coming up in chapter 4. Now, since this value is fairly close to 12, that again, as I mentioned before, tells us carbon-12 is the most abundant isotope. Okay, so just realize the average masses of all the isotopes in our mixture are determining the relative atomic mass. So these are the ones that occur naturally in these abundances on Earth. Okay, now we can in laboratories separate out specific isotopes. Oftentimes that is an expensive process. So if I were to purchase a fairly pure isotope sample of, let's say, carbon-12 or any other isotope on the periodic table, we can do so, but it's very expensive to isolate them from the other massed isotopes. And so if you're using that in a study, you're very careful not to mix it with samples that would contain the other isotopes, and you're very careful with the samples because of their cost. But in nature, we're not going to see them usually separated. We're going to see that mixture, so I use the relative atomic mass unless you're told you have an isotopically pure sample of a specific isotope that you're using that you might have purchased from a laboratory where they separated them. Now let's see how you could calculate a relative atomic mass. And to help you visualize this, I thought I'd start the sample with something you can see with the naked eye, because I'm assuming none of you have used an electron microscope yourselves or a tunneling microscope to see individual atoms with that instrumentation. But because of that, you haven't seen individual atoms or molecules usually, other than maybe a picture in a textbook or in our lecture slides. To help you visualize how relative atomic mass relates to an average of the mixture of different mass particles, I thought we'd look at an example problem where we look at a bag of marbles that has two different types of mass of marbles present in a mixture, and find a relative atomic mass that's basically the average weighted on percent of the mixed marbles in the bag. This is exactly, though, how I would calculate the relative atomic mass for a mixture of isotopes. Okay, so it's the same method. So let's see how we would do it for this bag of marbles with two different types of marbles. Okay. So I have two marbles in my mixture. Okay, there's going to be a lighter marble and a heavier marble. Now the first lighter marbles, let's say they're light blue in color, and they're going to be present as 40% of my mixture, the marbles in my bag of marbles, and each marble weighs on about 1.25 grams each. Now I'm going to have a heavier set of red marbles. These red marbles consist of 60%, let's say, of my marbles in my bag, and they weigh 2 grams each. So let's see what the relative mass would be. Now we can already make a slight prediction. Since I have a larger number of the heavier mass marbles, my relative atomic mass will favor being closer to 2 grams than being close to 1.25 grams. So I can make that prediction even before I get started. Whichever one's present in the larger percentage, I'm going to be a little closer with the relative atomic mass to that one. However, I do have 40% of the lighter marbles, so that is going to drop the relative atomic mass a little bit below 2 here. So let's go ahead and calculate that. Now, one of the things I want to do when I'm doing calculations to determine relative atomic mass, I usually want to take my percent values and divide them by 100. This will give me a fractional abundance of the marbles. So if I divide 40 by 100, I get 0.4 for my fractional abundance of the light marbles. If I divide 60 by 100, I'm going to get 0.6 for my fractional abundance for the heavier red marbles. So what I will do is take the fractional abundances times the mass of each and add them up. So here's how I set it up. I took the fractional abundance of the light blue marbles. So that 40% was divided by 100 to give me 0.4. And then I multiplied by the mass of the lighter blue marbles, 1.25. That'll give me a weighted contribution based on the original fractional abundance with respect to contributing to the relative atomic mass for the light blue marbles. Now if I take the 60% of the heavy red marbles, divide by 100, that gives me my fractional abundance of 0.6 for the fractional abundance here. And then if I multiply by the mass of the heavy red marbles of 2 grams, and if I add up these two terms, I find that the relative average mass of the marbles in my bag of marbles is 1.70 grams. And just as we had predicted, that's closer to 2 than 1.25 because there's a larger percentage of the heavier marbles in my sample. So on the periodic table, when we start looking at this, this also is telling us basically which of the isotopes present a larger amount with respect to which possible isotope mass we're closer to. Okay, so we're going to do the same type of calculation with a mixture of isotopes in nature. We'll look at some examples where we only have 2 isotopes, let's say, in a mixture that we're assuming, and we'll set it up in a very similar fashion. We'll take the fractional abundance of each isotope times their masses in atomic mass units, though, rather than grams. And we'll do that for every different isotope in the mixture, add them up, and that'll give us a relative atomic mass, which we should match if it's on Earth with respect to the percentages, should match the relative atomic mass on the periodic table below the element symbol. Okay, just remember I can look at my relative mass and it tells you which is the most abundant isotope, or in this case it's closer to the more abundant massed marble. Okay, the closer to the 2 grams of the heavy red marble. So I have more heavy red marbles than light blue marbles. Okay, since my periodic table is giving us the average atomic mass from these mixtures of isotopes, that's occurring because on Earth we usually have several isotopes present for different elements. Let's consider chlorine. If you look on the periodic table for chlorine, you'll see that it definitely is not close to a whole number. So we have 35.45 atomic mass units on average for the relative atomic mass of chlorine. So that's telling me I definitely have a few contributors to the atomic mass from different isotopes that we're looking at in a sample of chlorine. That's a bulk sample. If I were to do a calculation with this, it's useful to look up the mass of each isotope. And up to this point, we've been rounding the mass of isotopes to whole numbers. But realize it's only the carbon-12 isotope that's exactly 12 atomic mass units. Because the carbon-12 isotope was defined with respect to our atomic mass units, that an atomic mass unit was 1/12 the mass of carbon-12. As we start looking at other isotopes out there, they're not exactly a whole number, but they're very close. I'm going to measure their atomic mass units. Let's say that we've measured them maybe from mass spectrometry or other methods, and we found very carefully that their mass is going out to the thousandths place, and so I have a very careful mass of the isotope that I use in these calculations. Then in nature, I find out the relative abundance of each isotope. So here's the percent abundance of the chlorine-35 and the chlorine-37, which are the big players with respect to chlorine's isotopes in nature. What I want to do is take those percentages and divide them by 100 to get my fractional abundance, and then multiply them by the atomic mass units of that specific isotope that we have here. So I had to give you both of those sets of data in order to calculate the average atomic mass of chlorine, or the relative atomic mass of chlorine. I should be able to check my answer for this problem by seeing how close I match the value that's given on the periodic table. And you'll see it's very close to that value. But if I were to calculate it, here I have the fractional abundance of the chlorine-35. Right? I divided 75.77 by 100, so I have a fractional abundance of 0.7577. I multiply by the atomic mass units for a chlorine-35 isotope, so I'm taking 34.969 atomic mass units. And then for my second portion of this calculation, I'm going to take the fractional abundance of the chlorine-37 isotope, which is 24.23%, divide by 100. I get the fractional abundance of 0.2423. And then I take the atomic mass units of the chlorine-37 isotope and multiply by that. What that's doing is it's taking each of the two different types of mass isotopes, weighting them based on their fractional abundance, just like we did with the marbles, right? So I'm weighting the chlorine-35 isotope more heavily because there's more chlorine-35 isotopes in a sample on Earth in nature, so I'm going to be closer to 35 and not quite as close to 37. So if I go ahead and multiply fractional abundance by each of the masses of the isotopes and add that up, we'll find that we have a mass of 35.45 atomic mass units. Okay, now that's consistent with my mass I would see on my periodic table below the element symbol of chlorine. And so this is the type of set of measurements and calculations that had to be performed in order to find these relative atomic masses. But I won't always give you an element that's identified for you to look at the periodic table. In fact, I might make up a bogus element sometimes to see if you could do this calculation without being able to look up the answer. Let's practice finding the relative atomic mass of lithium. So I'm going to give you the percentages of lithium isotopes in nature and the average masses of those isotopes in atomic mass units. So my lithium-6 isotope is present at 7.42% in nature. It has an atomic mass for that specific individual atoms of those isotopes of 6.015 out to the thousandth place. Lithium-7 is 92.58%, and it has a mass of 7.016 atomic mass units in nature. If I go ahead and convert the percentages into my fractional abundances, I get 0.0742 for the fractional abundance of lithium-6. Getting that from this value divided by 100. It's color-coded in green. My fractional abundance for the lithium-7, color-coded in green. Once I divide by 100 from the percent, I get 0.9258. And if I take the atomic mass units for each type of isotope, so here's the lithium-6 isotope, here's the lithium-7 isotope, multiply them by their fractional abundances and add up each contribution, we'll get the relative atomic mass. And so we find for lithium that we have a relative atomic mass that we report on the periodic table of 6.942 atomic mass units. So this is how we can calculate those relative atomic masses. Now in all these cases you were able to see if you were getting the correct answer by looking at the periodic table, but as I mentioned before, I might give you a fictitious element that you don't know the answer to. So let's say we have a bogus element here. We're going to show the symbol capital B, lowercase o. This isn't an actual element here, so ignore any element symbols from the periodic table. And in this element, let's say there's 3 isotopes that contribute to the mass in nature rather than 2. So now we have one more level of difficulty since we have 3 isotopes present. So I'm going to need some data on all 3. I need the percentage of each of these abundances of the bogus element, the fictitious element. So I have my first isotope, which has a mass number of 10. That's 75.90%. My second isotope has a percent abundance of 8%. My third isotope, which has a mass number of 12, has a percentage of 16.10%. These, if I've accounted for all of the isotopes, should add up to 100%. Okay. I have the mass of each isotope given to the thousandths place. Okay, from this I can set up a calculation. Now the only difference between this calculation and the calculation we did for lithium and chlorine before to find the relative atomic mass is that you can't look up the answer to this one because this data was made up to test your ability to calculate it. And since we have 3 different component isotopes in the mixture, we'd have to do 3 portions of the calculation. So there's going to be 3 terms rather than 2. So I'm just going to do it a 3rd time rather than just the 2 times we've been doing on the previous problems. This would be a great point if you want to pause the video and try to do the calculation yourself and see if you're getting the right answer that I give you here in a moment. So go ahead and pause if you would like. Okay, so hopefully you've tried to calculate this on your own, and you're going to now see if you're getting the correct answer to the problem. So let's find what the average relative atomic mass for this bogus element would be. So first of all, let's look at the first isotope with a mass number of 10 for a bogus element. We're going to go ahead and take its percent abundance here, divide by 100 to get my fractional abundance. Okay, so I get a fractional abundance of 0.7590 for the mass number 10 bogus isotope. Then I'm going to multiply it by the mass of the isotope in atomic mass units here of 10.012 for the first isotope. And I'll repeat this for every one of the isotopes. So for my mass number 11 isotope, we take the fractional abundance of 8% divided by 100 gives me 0.0800 times its atomic mass units of 11.009. And then I can go ahead and take my third isotope, and so here's the new part to this calculation. We do it 3 times rather than 2 times. I take the 16.10% divided by 100, and I end up with having a fractional abundance of 0.1610, and I multiply by that by its mass number. Now I have 3 terms that have given me atomic mass unit masses for each isotope. Multiplied them to weight them based on their percent in nature. So I multiplied by the fractional abundance, and then I added each term up. And we would see as we add each term up that we have a relative atomic mass of 10.409. Okay, we're a little closer to the mass number 10 isotope than we are to the other isotopes, and that's because its percentage is the highest. So again, you can do a quick estimate just by seeing which whole number we're the closest to. We're the closest to 10. That frequently will give you an estimate as to which is the most abundant isotope. So isotope 10 is fairly abundant in the sample, even though I do have some others present at percentages of 8% and 16.1%. Okay, so let's consider a case where we give you the relative atomic mass, but we don't have the fractional abundance or the percent abundance of the isotopes we're looking for. So let's solve for unknown fractional abundances and unknown percent abundances of isotopes in a mixture. Let's consider a mixture that has 2 isotopes present. We're going to look at copper. I have the copper 63 isotope and I have the copper 65 isotope. I gave you the atomic mass unit for each isotope to 4 decimal places in this problem. We can look on the periodic table to find the relative atomic mass. So my average atomic mass of this mixture of isotopes in nature on Earth, my relative atomic mass, is 63.546 atomic mass units. With this information that I gave you, the mass of each isotope and the relative atomic mass, let's see if we can find out the fractional abundance of both of the isotopes. So this problem will have slightly more complicated algebra skills that you'll need to employ, which is why we had the prereq for the course that you've had college algebra level of mathematics before entering our course. So let's see if you can do this. So first of all, what I can imagine to try to solve for this problem, since there's 2 unknowns, I don't know the fractional abundance or the percent abundances of either isotope. So I have 2 unknowns to look for. So I'm trying to find the percent of the copper 63 isotope and the percent of the copper 65 isotope. I, however, know if those are the only 2 contributing isotopes that we're going to worry about for this problem. They should add up to 100% if we're assuming they're the 2 isotopes that are occurring in nature for the sake of working this problem. Now my fractional abundance, I would divide by 100 to each of these terms. So I had my 2 fractional abundances. I divide 100% by 100. So I could write fractional abundance for the 2. I'm going to color code the fractional abundance for the copper 63 isotope in an orange here, and the fractional abundance for the copper 65 isotope in yellow. But those fractional abundances should add up to 1 if we divided both sides by 100. Okay, now this is going to be useful. Rather than writing out fractional abundance of each isotope each time, let's write down an orange X for the fractional abundance of copper 63 and a yellow Y for the fractional abundance of copper 65. So I could rewrite this equation with an X and a Y as my variables. So X and Y is equal to 1 for fractional abundances. Now there's two unknown variables, but let's go ahead and relate Y to X. So I'm going to subtract X from both sides of this equation. So if I subtract X from this side, I'll have X minus X, so that will cancel X out on the left-hand side of my equation, and I'll end up with 1 minus X since I did the same thing to both sides of the equation. So I could write that my fractional abundance of copper 65, my Y, is equal to 1 minus my fractional abundance of copper 63, my orange X here. Okay, this is going to be a very useful equation because now we could insert 1 minus X for the variable Y for doing our calculation. So I have X plus 1 minus X is going to be equal to 1. That expresses our equation that relates fractional abundances to just the value X. So if we go ahead and solve for X in our calculation, we can solve for the fractional abundance of copper 63. And if I go ahead and take 1 minus the fractional abundance of copper 63, we'd know the fractional abundance of copper 65. So that's how I'm going to solve this equation. So we're going to set X equal to the fractional abundance of copper 63 in our calculations, and 1 minus X is going to be used, so we still use X as our variable for the fractional abundance of copper 65. So let's go ahead and set it up like we have in the past, but using these variables. Okay. So I've set up X as the fractional abundance of copper 63, 1 minus X as the fractional abundance of copper 65. Okay. I go to the periodic table, I find that my relative atomic mass of copper is 63.546. Okay, so I can set up my equation. I can say that the relative atomic mass is 63.546. That's going to be equal to my isotope masses for copper 63, and my fractional abundance of copper 63 is going to be multiplied by that. That's my X. And then we have my isotope mass for copper 65 times my fractional abundance for copper 65, which we just defined as 1 minus X. There's my equation. Just like we've been setting it up, we've been taking fractional abundances by the isotope masses. So we take the isotope mass here times the fractional abundance again. That's going to give me my relative atomic mass. We have to solve for X in this case. So we're going to have to do a little bit of algebra. So I'm going to go ahead and multiply my copper 65 isotope mass through my 1 minus X. And so I generate a new equation now. So 64.9278 times 1 gives me this term here. And then 64.9278 times a negative X gives me this term here. The rest of the equation is identical. Okay. We go ahead and we're going to collect terms. So let's collect the two terms with X. So I'm going to collect this term here and this term here and rewrite the equation. So here's still my relative atomic mass. Here's my term without X. Here's my term with X. We're going to isolate X. Okay. So I'm going to combine now the two terms, 63.456 and 64.9278 together. So I'm going to go ahead and subtract 64.9278 from both sides, which simplifies my equation down to 1.9882x is equal to 1.3818. Okay, if I divide both sides by 1.9882, I can isolate X, and so we find our variable X here, which is the fractional abundance of copper 63, as you remember, in orange. So my fractional abundance of copper 63 is 0.695. If we multiply that by 100, we get our mass percent of copper 63. So we'd end up with 69.5% of my sample must be the copper 63 isotope. Now to solve for the fractional abundance of copper 65, we need to take 1 minus X. So I take 1 and I subtract 0.695 from it. I end up with 0.305. This is the fractional abundance of the copper 65 isotope. Okay, if I go ahead and multiply by 100, that would give me my percent abundance of 30.5%, and so we end up with having my percent abundance of both isotopes. Okay, so this is how it is solve a problem where I'm trying to solve for two mass percents or fractional abundances. So be ready in case I put one of those on the first exam. You should be able to do this type of problem. This is about as challenging in a Chem 100 class as I would give. My more advanced students, I might give them 3 isotopes to have to solve for, but I'd have to give them a little more information. Now you're going to have a few homework problems that you're working on in this chapter, in chapter 2, which you might have to relate quantities that you have present in two samples. So let's say we have a sample of lithium atoms, and I have 7,000 atomic mass units of lithium atoms. So that's going to be quite a few lithium atoms, because a single lithium atom would be less than 7 atomic mass units, right? And then I have a sample that's 7,000 atomic mass units of nitrogen, and my nitrogen is going to be about 14 atomic mass units, and so I have quite a few nitrogen atoms in there. What we want to ask ourselves is which one of these samples contains more atoms? Is it the 7,000 atomic mass unit sample of lithium or the 7,000 atomic mass unit of nitrogen? Now you can usually, once you start to think about this, in your head make a quick prediction. Okay? If I consider that lithium atoms are lighter than nitrogen atoms, well, the lighter atoms I should have more of in a sample that's the same mass for the two. Think about it this way. If I had a bag of marbles that weighed 7 grams with light marbles or 7 grams with heavy marbles, well, the sample that had more marbles in it obviously would be the 7 grams with the lighter marbles. Okay? If I have 7 grams of the heavier marbles, it would take fewer of those marbles to add up to that 7 grams. It's the same thing here. It takes fewer of the heavier atoms, the nitrogen atoms, to add up to the 7,000 atomic mass units, and it takes more of the lighter atoms, the lithium atoms, to add up to the 7,000 atomic mass units. So I should have more lithium atoms. But let's try to convince ourselves. Let's do a quick calculation to try to convince ourselves of this. So I look up the relative atomic mass units of lithium, because I'm going to have several lithium atoms here. I'm going to get a mixture of its isotopes for the calculation. So I look on the periodic table, lithium 6.94 atomic mass units for its relative atomic mass. I look up the relative atomic mass unit to 2 decimal places for nitrogen. It's 14.01 atomic mass units. Let's calculate how many atoms in each sample to see if we're right with our prediction. So I take 7,000 atomic mass units of my sample size, and I divide it by the relative atomic mass unit for lithium atoms, so 6.94 atomic mass units. It tells me that in this mixture that I have roughly 1,009 lithium atoms. We have close to that. Okay, if I take 7,000 atomic mass unit sample size for the nitrogen and divide by the relative atomic mass unit of the heavier nitrogen atoms, you're going to see I have fewer, right? That's our prediction. We end up with only about 500 nitrogen atoms roughly. Okay, so we have fewer nitrogen atoms in our sample of this mass than we would have of the lighter lithium atoms. And so you should always predict that. The lighter atom or molecule in samples that are the same mass, you'd have to have more of to add up to that mass. That makes complete sense, doesn't it? Okay, so you have some homework problems related to that. You do have one homework problem that uses the scientific notation, which we'll talk more about in Chapter 1. But let me help you with this. So let's say we have 5.30 times 10 to the 9th atomic mass units. Now that's in scientific notation. Remember, the 9th, since it's a positive value on my scientific notation for this exponent, means that we had a very large value and had moved the decimal place to the left 9 times to generate the scientific notation. If I want to convert it back to a regular number, to one of the large number it was to begin with, I can take it out of scientific notation by moving the decimal place. When I have a positive superscript here, I move the decimal over 9 times to the right. So I get a very large number of atomic mass units for my sample of carbon. So let's calculate how many carbon atoms I would have in this sample. So I went ahead and converted the scientific notation to a standard number for you. Remember, I just moved the decimal point over to the right 9 times. I knew to move it to the right because I have a positive value. If you had a negative value for scientific notation, we'd move it to the left to convert it to a standard number. So I end up here having my 5,300,000,000 atomic mass units. If we take that sample size and divide by the atomic mass units of carbon, and I'm using a relative atomic mass because we have a sample that's going to have a lot of carbon atoms, so I didn't want to just use a specific isotope mass. I used the relative atomic mass unit. I divided that into the size of my sample. It tells me here that I would have to have 4,410,000 carbon atoms to add up to this mass. Okay, so we were able to do a calculation. This is just a much larger sample size that we were dealing with than when we dealt with those 7,000 atomic mass units on the previous sample. Okay, for the last part of our lecture today, I'd like to look at ions a little bit. So make sure you keep practicing with the relative atomic mass units so you're comfortable with using them and looking them up on the periodic table and relating them to mixtures of isotopes. But let's go back and review for just a second what we had covered when we discussed classifying elements on the periodic table in that previous lecture. If we consider our group 1, remember our groups or families are columns on the periodic table. So my group or family here, groups a more modern term, families used in some older textbooks, or some textbooks introduce you to both, but it's my column on the periodic table. My group 1 or 1A, those are my alkali metals, and they always form cations that are stable with a +1 charge. In fact, we don't expect the alkali metals to form any other charged ions that are stable. So they have all lost 1 electron to form that +1 charged ion. So they have done that in order to have the same number of electrons as the noble gas before them, because the noble gases before them have a very stable set of electrons. So they lose 1 to have the same number. Now my group 2, my column 2 or 2A, my group 2 or 2A, those are my alkaline earth metals. They would all have to form a stable set of electrons, like the nearest noble gas. They would have to lose 2 electrons, and so I expect the alkaline earth metals would always form +2 charged cations, and no other cation charge would be expected to be stable for them. So if I remember group 1, I'll form +1 charged cations. Group 2 always forms +2 charged cations. I already have all of those monoatomic ions memorized. Monoatomic, if you recall, means a single atom that has formed an ion. So those are the ions we expect these atoms to form that are stable. So I know those charges already. We also know that the halogens, right, fluorine, chlorine, bromine, iodine, form the fluoride, chloride, bromide, iodide ion. We changed the ending of their name to indicate they're a monoatomic ion. And they have formed -1 charges as their only stable anions that they would form, because they would like to gain 1 more electron to be like the noble gases in group 18 or 8A. My oxygen family, oxygen, sulfur, selenium, and tellurium, they would like to gain 2 electrons. They need to gain 1 and 2 to have the same number of electrons as the nearest noble gas. So I can remember group 16 or 6A always forms monoatomic ions that are a 2- in charge. My nitrogen and phosphorus, they like to gain 3 electrons, 1, 2, 3, to be like the nearest noble gas. So they form negative or a 3- charge on their ions. Carbon forms a 4-, so this would be carbide. The monoatomic nitrogen anion would be nitride. The monoatomic phosphorus anion would be phosphide. So you should know from these groups that I've shown you here for alkaline metals, alkaline earth metals, and the non-metals here shown in red, they always form these specific charges. We don't expect any other charged ion to be stable for these elements. Okay. However, do realize that some of them can form, for these non-metals, polyatomic ions, where we have a group of atoms with a charge, and those polyatomic ions usually will not have an IDE ending. They usually will have an ATE ending or an ITE ending when they've combined with oxygen to form a polyatomic ion. So just be aware that we're going to see some more complex ions coming up in the next chapter. Now there's a few other ions you should know. You should know silver always forms a +1 charge, zinc always forms a 2+ charge, aluminum always forms a +3. It's easy to see with aluminum it would like to lose 3 electrons, so it would lose 1 to be like magnesium, 2 to be like sodium, and the 3rd electron will make it like the nearest noble gas, which would be neon in the noble gas family. So it makes sense it would form +3 charges. You just need to memorize those. Zinc's +2, silver's +1. Notice a nice stair step here though. 1, 2, 3 for silver, zinc, and aluminum. Really easy to remember if you remember that trend on the periodic table. You must also remember cadmium only forms 1 stable charge state, just like zinc, it forms a 2+. So you need to remember silver, cadmium, zinc, aluminum only form 1 possible charge state. Now, any other metal on the periodic table that I have not discussed up to this point can have multiple possible charge states. The ones I've shown here are some common transition metals and metals below the metalloid line like tin and lead. These are the common charges that they form, but they can form a variety of charges. For example, tin and lead not only form the 2+ cation, they can also form 4+ cations. So we're going to see a variety of charges on some of these other ions. You have to be given a little information. In their names, you would use Roman numerals to indicate, well, out of the variety of charged cations they can form, which one is it? So I could say tin 2 or lead 2 with Roman numerals in their names to indicate which charges they have. Or I could have a tin 4 if I have the tin 4 cation, or a lead 4 if I have the lead 4 cation. If I have iron, I'd use Roman numerals to indicate either iron 2 or iron 3 to indicate the charge. Or there's some older naming systems where I would name iron 2 ferric and iron 3 ferrous, which we'll be seeing in chapter 3 as well. So all these others can have a variety of charges. Nickel can have a variety, but copper 2 is the one you see the most of. Chromium can have a variety of cation charges, but chromium 3 is the one you see the most of. It's kind of useful to know some common charges that they form, but make sure you learn the ones that only form one possible charge first. Okay, so with that in mind, let's look at a few predictions we can make. Let's predict how many electrons a sodium cation would have. Now, if I have a neutral sodium atom, if I look on the periodic table, there are 11 protons in a neutral sodium's nucleus, and that won't change when I form an ion, right? It's the electrons that change when I form an ion. However, the neutral sodium should have had the same number of electrons. It would have had 11 electrons, and when it formed the sodium plus 1 charged cation, we've lost 1 electron. So we have 1 more proton than the number of electrons, and so we would have to have only 10 left at that point. Now you notice that the magnesium cation, before it formed a cation, the neutral magnesium atom should have had 12 electrons to be equivalent to the number of 12 protons in its nucleus. I'm looking at the periodic table for its atomic number to predict the protons in the nucleus. So if I subtract 2 from 12, I would have had to lose 2 electrons to form the plus 2 charge cation. You'll notice it has 10 electrons left. Now the aluminum, let's go get to the other side of the transition metals portion of the periodic table. So I'm looking at atomic number 13 for aluminum. If it's a neutral aluminum atom, we would have 13 electrons when it forms the aluminum cation with a 3 plus charge is what we learned. It would have to lose 3 electrons. Well, look at this. It has 10 electrons left. We're seeing a trend here. We're seeing that these elements all have 10 electrons left when they form a stable ion. Perhaps there's some stability about having these 10 electrons at this point. Later on, we will learn to look at what are called electron configurations, and you'll learn some rules to predict stability. But for right now, let's just look at the numbers and see how this trend continues. Let's look at oxygen. Now, oxygen is the 8th element on the periodic table. It has an atomic number of 8. When it's neutral, it has 8 electrons. However, when it forms a stable anion with a negative charge, it likes to form a 2-. It does so by gaining 2 electrons. So we went from 8 electrons, we gained 2 more. We have 10. We're seeing this trend continue when we're looking at these elements around this same portion of the periodic table. Now, fluorine, neutral fluorine would have had 9 electrons. However, when it forms fluoride, the fluoride anion must gain 1 more. So they have 10. So all of these ions are stable when they form a charge that gives them in the end 10 electrons. As I said before, they're trying to form a stable, basically, set of electrons that are the same as the nearest noble gas. So let's look at the nearest noble gas. Well, oxygen and fluorine have neon as the nearest noble gas after them. Aluminum, magnesium, and sodium, the nearest noble gas before them is neon. So this is why we're seeing the same number of electrons when they're stable. That's because neon, when it's a neutral atom, has 10 electrons. Neon is fairly inert. It doesn't like to lose or gain electrons readily. So it's very stable with the 10 it already had. So we can see that cations like to form charges that will give them the same number of electrons as the nearest noble gas if they can, if it requires only a few electrons to be lost. Or the nonmetals would like to gain electrons to form anions when they're near the noble gas, to form the same electron configuration, the same number of electrons as the nearest noble gas. And so that allows us to make some predictions. So I wanted to show you that, so you start thinking about that. This would work for other periods on the periodic table too, though another noble gas like argon or krypton might be closer in those cases. Okay, so let's write a few symbols for ions that we predict to be stable. So if I ask you what is the stable ion that forms for lithium, well, I should look on the periodic table. It's in group 1. It's an alkali metal. It's going to want to lose 1 electron to be like the nearest noble gas before it. In this case, that would be helium. So I would predict, since it's in group 1, it forms a charge that's equivalent to that group number in this case, forms a +1 charged cation. So there's my symbol. For beryllium, we would end up with beryllium, since it's an alkaline earth metal, group 2, it would need to lose 2 electrons to be like the nearest noble gas. I expect metals to form cations anyway, so I form the beryllium 2+ cation. Now if we look at aluminum, so I'm going to show you a portion of the periodic table over on the other side. If we look at aluminum here, well, remember aluminum's in group 13 or 3A. If you have a periodic table that has these Roman numerals like 3A, that often reminds you what charge aluminum will form. So aluminum will lose 3 electrons. It's a metal. We expect to form a cation. It loses 3 electrons to be like neon before it, just as we were seeing on the previous example. So I write the symbol for aluminum, and I can remember it only forms a stable charge of +3. It starts that stair step at the top. If I go down and to the left, we'd get to zinc, which is +2. Down to the left again, we get to silver, that's +1. If I look underneath zinc, there's cadmium. It's the same charge as zinc. It's a 2+. I need to remember those only form one possible charge state. I would never use Roman numerals in their names because only one charge state is stable, so they don't need Roman numerals. If we consider nonmetals like phosphorus, well, phosphorus is a nonmetal, so I expect to form an anion. And anions are forming due to negative charges as they gain extra electrons. So I have 1, 2, 3 electrons that are gained to be like the nearest noble gas, which would be argon. So I would change the ending of the element name as it forms an anion to an ide when it's a monoatomic ion. So this would be called phosphide once it forms the anion. So I show a P3- indicating 3 electrons were gained. If I look at chlorine, well, chlorine only needs to gain 1 electron to be like argon, to have 18 electrons. We changed the ending of chlorine's name to an ide, so I would call this chloride, and so we have a Cl-. Okay. If we look at oxygen, well, oxygen would like to gain 1, 2 electrons, so it goes from 8 electrons to 10 to form an anion. Non-metals we expect to do so. So the monoatomic ion we call oxygen oxide once it forms an anion. And so it's a 2-. So we were able to predict all those charges. And remember, you can use your periodic table to predict a lot of these common charges to make your life easier in these types of problems by their location. The nonmetals, if you want to predict charges another way other than just predicting how many electrons to be like the nearest noble gas, you could also take the group number 15, 16, or 17, subtract 18 from it. So if I have fluorine, I can take 17 minus 18, gives me a -1. It tells me fluoride would be the charge would have a -1. Okay, so I can use that.